Welcome back. Today, we're going to dive into one of the most important ideas in all of modern AI. It's a technique that started out as just a clever way to make things faster, but it morphed into a way for machines to actually understand meaning itself. Let's get into the incredible story of vectorization. It sounds a little like the start of a strange joke, right? Dicing peppers, deep learning, the sound of waves. What on earth could connect all these things? Well, by the end of this explainer, you're going to see exactly how they're all tied together by one single powerful idea. All right, so to really wrap our heads around this, we're not going to start with a supercomputer. Nope. We're going to start in a kitchen with a task that's about as simple and everyday as it gets. But before we even start dicing, let's just zoom out and understand why we even need a new way of thinking. The problem really is scale. I mean, we are creating an absolutely unimaginable amount of data every single second. Our old ways of processing it all, they just can't keep up. We need to work smarter, not just harder. And our little kitchen problem is going to show us exactly how. So this slide just lays it out so perfectly. First, you've got the normal sequential way of doing things. One chef, dicing one pepper at a time. It works, but it's slow. Then you have parallel processing. You just hire more chefs and split up the work. Sure, it's faster, but now it's more complicated. But that third option, that's the real game changer. You don't get more chefs, you change the tool. One chef, one food processor, and all 12 peppers are done in a single go. That, right there, is the core idea behind vectorization. So here's the key takeaway. Vectorization is all about doing the exact same thing to a whole bunch of data all at once with just one command. It's a huge shift from doing things one by one to just doing everything at once. Okay, so the kitchen analogy is fun, but what does this actually look like when we're talking about real code? Well, the difference in performance is, honestly, it's staggering. On the left, you've got the classic for loop. This is you telling the computer's processor, hey, go get one item, do this thing to it, then go get the next item, do the same thing, and on and on. It's the knife, one slice at a time. But on the right, you have a vectorized command, maybe from a library like NumPy. It just bundles everything up and says, do this to the entire batch right now. That's the food processor. And the result? Well, in one test from Deep Learning AI, they ran a calculation on 1 million numbers. The for loop took almost 500 milliseconds. The vectorized version? Just 1.5 milliseconds. That is over 300 times faster. And we're not talking about a small tweak here. This is the difference between your code finishing in 1 minute or you having to wait 5 hours for it to finish. So here's the golden rule for anyone working in data science or machine learning. Modern computer chips, from the CPU in your laptop to the crazy powerful GPUs and gaming cards, they are literally built for this kind of work. Single instruction, multiple data. When you avoid those slow step-by-step loops and use vectorized code, you're finally unlocking the real power of the hardware you already have. Now, if the story stopped right there, vectorization would just be a really, really brilliant optimization trick. But this is where the whole idea gets truly profound. This is where it evolves from just a simple speed hack into something much, much bigger. For a long time, the answer to that was basically, yeah, it was about making math go faster. But then people started asking, what if those lists of numbers, those vectors, what if they could represent more than just quantities? What if they could actually represent concepts? What if they could hold meaning? And this leads us to the incredible idea of embeddings. Basically, a neural network learns to turn anything you give it, a word, an image, a sound, into a long list of numbers, which is just a vector. You can think of that vector as a single coordinate on a giant invisible map. And the network's whole job is to put things with similar meanings close to each other on that map. So the vectors for cat and lion will be neighbors, while the vector for car will be way off in another continent. It's literally a map of meaning built entirely out of numbers. And what's just wild is what we can turn into these meaningful vectors. It's not just words and pictures. We can create embeddings for sounds, for 3D depth information, for heat signatures from a thermal camera, even for the motion data coming from the little sensors in your phone. So, okay, if we can turn almost anything into a vector that captures its meaning, what can we actually do with that? Well, this takes us to a groundbreaking project from Meta AI called ImageBind. The central idea of ImageBind is something we all kind of understand intuitively. Images are this powerful hub for all of our senses. right? You see a picture of a beach, and it immediately connects to the sound of waves, maybe the text of a poem about the ocean, or even the feeling of a breeze. Images can be the bridge, the thing that binds all these different kinds of data together in one single shared space of meaning. And the way they did it is just so elegant. First, they only train a model on pairs of images and text, so it learns to connect a picture of a beach with the words sandy beach. Then, in a totally separate step, they train it on pairs of images and audio, so it learns to connect that same beach picture with the sound of waves. Now here's the magic part. They never explicitly train the model to connect the text and the audio. The model just figures out that connection on its own because they both relate to the same image. They call this emergent alignment. And because everything lives in this one shared space, you can start to do a kind of conceptual math. You can take the vector for an image of fruit and literally add the vector for the sound of birds. And the result is a brand new vector that represents the idea of fruit on a tree with birds. I mean, you are doing arithmetic with ideas. How cool is that? Okay, so we've created this incredible unified map of meaning, and it has billions of ideas on it, all represented as vectors. But that creates a huge new challenge. How do you search the space? If you're looking for something, how does the computer efficiently find the closest, most relevant vectors when there are literally billions or even trillions of them to check? Just going through them one by one is way, way too slow. This is exactly where tools like FACE come into play. It was developed at Meta AI, and FACE, which stands for Facebook AI Similarity Search, is an open-source library that is designed specifically for this one problem. You can think of it as a hyper-efficient search engine for these giant maps of meaning. And this slide really gets to the core challenge for any vector search library. It's all a fundamental trade-off. You can't have everything perfect all at once. You can choose to get a very, very fast answer that's mostly accurate, or you can wait longer for a perfect answer. You can also compress the vectors to save memory, but that might cost you a little bit of precision. It's this constant balancing act between speed, accuracy, and memory. So let's just step back for a second and bring all of this together, because the journey this one idea has taken is just incredible. We started with a super simple goal. How do we process a bunch of numbers faster? Like dicing peppers with a food processor. But that simple speed trick unlocked something so much more powerful, the ability to represent pretty much anything as a vector and place it on a universal map of meaning. We went from building a speed machine to building a meaning machine. And this really leaves us with a final, fascinating question. As we get better and better at turning everything imaginable into a vector, from smells to brainwaves to complex scientific data, what new hidden connections about our world are just sitting there waiting for us to find them? That is the future that this incredible technique is building right now. Thanks for joining me.